So today in this class we will talk about divisibility, its definition, and its simple basic properties. So let us start with the definition of divisibility. An integer b is said to be divisible by an integer a which is non-zero if we can find another integer c such that a dot c equal to b and we write this as a divides b or b is divisible by a. Read it as a divides b. So a divides b means we can find c, an integer, such that a dot c equal to b. This is the basic definition. Now some results, basic results. We will state them along with their proofs. First one is, for any integer a divides 0, we have a divides 0, 1 divides a, and the number itself divides a. That means it divides itself. These are basic three results. These are not assumptions, and these can be proved by using the definition above. So this is clearly true because as a multiplied by 0 is equal to 0. This implies a divides 0. So any number divides 0. Now 1 divides a. That means 1 multiplied by something gives us a, and 1 multiplied by a is a. So 1 divides a. Also a divides a, that means a multiplied by something gives us a, and which is precisely 1. So a divides a. So this is it. Now we also know any number which divides 1 is plus or minus 1. If a divides 1, then a is equal to plus or minus 1, and conversely. How to prove this one? So suppose a divides 1. Let a divides 1. Then there exists C, an integer such that a dot C is equal to 1. That's the definition of divisibility. Now if a is not equal to plus or minus 1, then C is also not equal to plus or minus 1, or if mod C is not equal to 1, then as it is always positive, mod C will be greater than 1, and we also have taken mod A to be greater than 1. If A is not equal to plus or minus 1, then mod A is also greater than 1 and mod C is also greater than 1. Then what will happen? Mod A multiplied by mod C, which is mod of AC, is greater than 1. And it is a contradiction. It is a contradiction to the fact that A multiplied by C is 1. So our assumption that mod C is not equal to 1 is false. Therefore, mod C is equal to 1. That is C equal to plus or minus 1. Now, if C equal to 1, then A multiplied by C equal to 1 implies A multiplied by 1, which is equal to A, is equal to 1. And if C is equal to minus 1, then A multiplied by C1 will imply A multiplied by minus 1 equal to, which is equal to minus A, is equal to 1, or A equal to minus 1. Both of these implies A equal to plus or minus 1. So this is it. So we have to prove conversely also. I think this is if and only if. So conversely, let A equal to plus or minus 1. Now if A equal to 1, then A into 1 is equal to 1 into 1 is equal to 1. So A divides 1. If A equal to minus 1, then A into minus 1 is equal to minus 1 into minus 1, which gives us 1. And this again implies A divides 1. So in any case, we have a divides 1, and this completes the proof that a divides 1 if and only if a equal to plus or minus 1. This is it, and again next result is, I think this is result 3. If A divides B and C divides D, then AC divides BD. Prove that if B is divisible by A and D is divisible by C, then product of B and D is divisible by product of A and C. This is also pretty straightforward. The object of this doing these proofs is to know how to use the definition of divisibility. So given A divides B means there exists an integer x such that A dot x is equal to B. From definition, again from definition we have C divides D means there exists an integer y such that C dot y equal to D. Now multiplying B and D, we have AC into xy equal to BD. I have just rearranged the terms using the associativity of integers. This says AC into something equal to BD, that means AC divides BD. This is the definition of divisibility from definition. Okay. Pretty clear. Then there are 2 or 3 more results. This is an important one. If A divides B and B divides A, then A equal to plus or minus B, and this is if and only if. And to show this one, we'll use the definition. Let A divides B, then there exists an integer x such that Ax equal to B, and B divides also A. That means there exists an integer y such that by equal to a, and putting the value of b from above equation, we have axy equal to a, or by left cancellation, which holds in set group of integers, we have xy is equal to 1. And we have proved that xy equal to 1 means x is equal to either one of them must be plus or minus 1. So this says x divides 1, or which is same as saying x is equal to plus or minus 1. So if x equal to 1, then when x equal to 1, then ax equal to b implies a equal to b. When x equal to minus 1, ax equal to b implies minus a equal to b, or a equal to minus b. Both of these cases says a equal to plus or minus b. This is one way. Another way of saying will be, let a equal to plus or minus b. Now when a equal to b, then how to write this one? Okay, we want to show that a divides b. Then a into 1 is equal to a, which is equal to b. A into 1 is equal to a. So a into 1 equal to b we have. And this says a divides b. Again, b into 1 is equal to b, which is equal to a. This says b into 1 equal to a. That means b divides a. It is important to see the application, repeated application of the definition. So we got our result that a divides b and b divides a when a equal to b, and when a is equal to minus b, we can do it similarly. A multiplied by minus 1 will give us minus b into minus 1, which is b. So this says a divides b, and for b divides a, we have b multiplied by minus 1. B is equal to b multiplied by minus 1 is b minus b, and this is a. So b multiplied by minus a, we got a. So we have b divides a. So in either case, we have A divides B and B divides A. So we proved A divides B and B divides A implies and implied by A equal to plus or minus B. So this is again another result. Let us prove two more results. If A divides B and B is non-zero, then the absolute value of A is less than or equal to the absolute value of B. This is again well-known result. We are just stating the known results and proving by using our definition. So how to prove this one? Given A divides B, that means we can find an integer C such that A multiplied by C is equal to B. Now we also are given that P is non-zero. That means A dot C is not equal to 0, and which implies C is not equal to 0, as we already have A is non-zero. So both A is non-zero and C is non-zero. C is non-zero means mod C is greater than equal to 1. As always, modulus is greater than equal to 0, and C is non-zero, that means it is greater than equal to 1. Now mod B is equal to mod of AC, which is mod A mod C, and this is greater than equal to mod A. That is, we have mod A less than equal to mod B. That's it. So whenever a number divides another number, it must be less than equal to that number, at least their absolute values. Well, its absolute value will be less than the dividend. The absolute value of divisor is always less than the absolute value of dividend. We know this one. Just trying to prove without taking any particular example. Next result is, this is also we know, if A divides B and A divides C, then A divides the linear combination. A divides Bx plus Cy, where x and y are arbitrary integers. So this is also a well-known property to watch. Now how to prove this one? So given A divides B and A divides C implies there exist integers C, say R and S belonging to Z such that AR equal to B and AS equal to C. Now BX plus CY equal to ARX plus ASY, which is equal to A RX plus SY. So we have A multiplied by Rx plus Sy is equal to Bx plus Cy, that which says A divides Bx plus Cy. This is it. Here Rx plus Cy is an integer. Rx plus Cy is an integer. I think this also concludes our proof. The converse is not true. The converse of the is not true. Example, we could take anything. For example, say what can we take? Okay, x and we can take x and y to be 1. Make both of them 1. Say let A equal to 3, B equal to 2 and C equal to 7. So A divides B plus C, that is 3 divides 9. But A does not divide B and A also does not divide C. So the converse is not true. Next, now let us do some questions or exercises. Exercise questions. Question number 1 says, prove that for any integer A, one of the integers A plus 2, A plus 4 is divisible by 3. We want to prove this one. It says, given any integer A, these three numbers, out of these three, one will be divisible by 3. So for example, we could take any integer, say a equal to 7. Then a is not divisible by 3. That means 3 does not divide, say 3 divides a plus 2, which is 9, and 3 does not divide a plus 4, which is 11. Taking another number, say a equal to 5, then 3 does not divide a, 3 does not divide a plus 2, which is 7, but 3 will divide a plus 4, which is 9. And this is true for any integer. You can verify that. Now we have to prove this one, and the proof is lengthy one, but it is rather straightforward from the division algorithm and definition, our definition of divisibility. Okay. Proof. There will be three cases. We will take any arbitrary, any of these three. Say we will take a, then a plus 2, then a plus 4, and say they are not divisible by 3. Case 1 is, suppose a is not divisible by 3. That means 3 does not divide, say. Then from division algorithm, we have a equal to 3q plus 1 or a equal to 3q plus 2. R is either 1 or equal to or 2. It cannot be 0 as it is not divisible by 3. Now when a equal to of the form 3q plus 1, then a plus 2 is equal to 3q plus 1 plus 2, which is 3q plus 3, or 3 into q plus 1. That means 3 divides a plus 2. You can verify that a plus 4 is not divisible by 3. When a equal to of the form 3q plus 2, then a plus 4 is equal to 3q plus 2 plus 4 is equal to 3q plus 6, and it becomes 3 into q plus 2. This again implies 3 divides a plus 4. So in either case, the other two, or one of the other two, is divisible by 3. When a is not divisible by 3. So when a is not divisible by 3, either a plus 2 is divisible by 3 or a plus 4 is divisible by 3. Then going to case 2, suppose 3 does not divide a plus 2, or a plus 2 is not divisible by 3. Then a plus 2 is equal to either 3q plus 1 or 3q plus 2 by the same argument as above. Then a becomes 3q minus 1, and a plus 4 becomes 3q plus 3, which is 3 into q plus 1. So 3 divides a plus 4, or a plus 4 becomes divisible by 3, and a is not divisible by 3. This is case 2. This is when a plus 2 equal to 3q plus 1. This is when a plus 2 is equal to 3q plus 1. When a plus 2 is equal to 3q plus 2, then a becomes 3q. This is 3 divides a. This is case 2. So either a is divisible by 3 or a plus 4 is divisible by 3. When a plus 2 is not divisible by 3. I think I am clear. Similarly, we can show that you can try it. We can show that when a plus 4 is not divisible by 3, either a is divisible by 3 or a plus 2 is divisible by 3. So I think we are done. Let us do one more question. Prove that for any integer a, a into a plus 1 is divisible by 2, and a multiplied by a plus 1 multiplied by a plus 2 is divisible by 3. Let us first of all understand the statement, two bits. First one says product of two consecutive numbers is always even, and the second one says product of three consecutive numbers is always divisible by 3. Rewriting the statements: product of two consecutive integers is even and divisible by 2. Product of three consecutive integers is divisible by 3. You can generalize this statement. Product of four consecutive number is always divisible by 4, and like that. But these two statements are true. Now, how to prove this one? The first bit is rather easy, then the second bit. Prove. Given any integer a, we have by division algorithm either a is even or odd. A equal to 2q okay. A equal to okay. I think I am facing some difficulties here. A equal to 2q or A equal to 2q plus 1. When A equal to 2q, this is from division algorithm, it says either a integer is even or odd. When A is odd, then A into A plus 1 becomes 2q into 2q plus 1, and this clearly says 2 divides A into A plus 1. When A equal to 2q plus 1, A multiplied by A plus 1 becomes 2q plus 1 into 2q plus 2, and which again says 2 multiplied by q plus 1 and 2q plus 1. So this again shows 2 divides A into A plus 1. This is due to this A. This is this 2. 2 into something. A into A plus 1 is equal to 2 into something. So that's it. This is the proof of bit 1. Then going to bit 2, we have again by division algorithm. Now we are going to take 3 instead of 2. A equal to 3q or 3q plus 1 or 3q plus 2. When A equal to 3q, it is clear. It is clear to us that the product will be divisible by 3. A into A plus 1 into A plus 2 becomes 3 into q into 3q plus 1 into 3q plus 2. This is 3 divides the product. When A is equal to 3q plus 1, again the product becomes 3q plus 1 multiplied by 3q plus 2 multiplied by 3q plus I think 3, and taking a 3 common here, okay, this is 3 divides the product. Again, when a equal to 3q plus 2, the product becomes a into a plus 1 into a plus 2 equal to 3q plus 2, 3q plus 3, and this is 3q plus 4, and this is equal to 3 into q plus 1 multiplied by the rest, which again says the product is divisible by 3. This is the end of our proof. You could try by using the same methods other questions from our exercise. So try it yourself. Questions: 3 divides a multiplied by 2a square plus 27, where a is an integer. Then 32 divides a square plus 3 and a square plus 7 for all odd integers. Then try to prove 16 divides a power 4 plus b power 4 minus 2 for all odd integers again. So आज ପାଇଁ ଏତିକି. We'll discuss greatest common divisor and its applications in the next class.